Welcome to the Math Methods 3 and 4 revision video on Chapter 18, the normal distribution. As per our previous video, please note the questions and examples used in this video are taken from the Cambridge Essential Mathematical Methods 3 and 4 CAS textbook. No intention has been made to infringe copyright, and my apologies if it has. This is simply a video resource for my current students to assist in their preparations for their VCE examination. Thanks for understanding. Okay, so let's make a start. Previously, we were talking about the ideas of probability density functions, or probability distribution functions, if you were listening to my last video and I had no idea what I was talking about. Today we move on to something called the standard normal distribution. So what is the standard normal distribution? Well, if we look at the diagram I've just put on the screen, then what we find is it's a density function, or probability density function, which is centered around 0. That means our mean is at 0. And as we've previously looked at, we have this graph can be split up into 3 main sections either side. Now these are our standard deviations, right? So there's one standard deviation, 2 and 3, and this is -1, -2 and -3. Now our standard normal distribution, as usual, we would like for it to have an area of 1 under our graph, which then helps us with our probabilities. So we use this standard normal distribution in the same way as we used our probability density functions to try and find probabilities of various things happening. But what we find is this graph actually has some very interesting characteristics, and the fact that it has a mean centered at 0 and it has standard deviations of 1 is quite useful to us. This particular equation, or this particular function, has its own equation, which can be given by the function of x is equal to 1 over the square root of 2 pi times e to -1/2 of x squared. Right? That's quite important, and we need to know that formula, or at least the general form of it, to help us with later questions. Now, sadly, not all probability density functions look like that. Wouldn't it be great if we could try and transform, or knowing some properties of one probability density function, try and transfer it into this here, or transform it into this particular shape? Well, let's look at how we might be able to do that. Imagine we have two density functions, probability density functions. Now, the first thing I'm going to say is this one here is our standard normal distribution. Right? It has a standard normal distribution. It's centered around 0, which is our mean, and it has standard deviations of just 1. So our mean, which we know is mu, is equal to 0, and our standard deviation is equal to 1. However, here on this graph, or our purple graph, we have a probability density function which has a mu of 10 and a standard deviation of 2. How can we see that? Well, we know that this value here, our highest, is 10, or rather is centered around 10, and we can see that the gaps that I've written on seem to have 2. I haven't written the values on either side of our normal, just so that we can sort of keep the diagram clutter-free. But one of the interesting things is, how do we work out our transformations, our translations, as it were? Well, what I've decided is, if we look here at the idea of our standard deviations, they are centered at 0, 1, 2, and 3. For this graph here, they seem to be at the values of 0, 1, 2, and 3. That's great, our standard normal distribution. What happens if we look at our probability density function? Well, we can see that they seem to be centered at 10, 12, 14, and 16. And hopefully it won't take a huge genius to realize, well, what we seem to be doing is, for our 1 value, so if we look at this value here, our first standard deviation, so the value of 1, goes to the value of 12. What does the value of 2 go to? Yep, it goes to the value of 14, and the value of 3 goes to 16. So how can we then look at that in terms of translation from, or transformation from each of these values? Well, what seems to be happening is we have our x and y values seem to be going along the lines of, right, well, we seem to be taking our x value and multiplying it by our standard deviation, and then adding on 10, which is our mean, right? So let's just take that. Our x values are multiplied by the standard deviation, all right? and then they have the mean added on. So 1, so our standard deviation was 2, so 1 times 2 is 2, plus 10, because this whole thing has gone from centering around 0 to centering around 10, and that seems to work. But what about our y? Because we've realized that the area under here, right, the area under this graph here, we want to keep exactly the same as the area under this graph, or our standard normal deviation. Well, we know the formula for our standard normal deviation was given before, and we know that this whole graph is effectively being squeezed in by a factor, or rather it's being stretched by a factor of sigma. So if this graph is being stretched by a factor of sigma in the x direction and we're trying to keep it effectively proportional, then what we find is our y value is divided by sigma. All right? So that is pretty much our formula. To map from the standard normal distribution onto our normal distribution, we use this idea here, right? So you take your x values, multiply by sigma and then mu, and our y values are divided by sigma. Well, that seems pretty interesting. Is there a way of doing it backwards? Well, what we can do forward in maths, we obviously can do backwards. So how do we go from our normal distribution and map it onto our standard normal distribution? But if our normal distribution has coordinates x and y, then what does that mean we have to do to get vice versa? Well, we take our x value and we minus our mu value and divide it by sigma, right? So let's just check. So I've got 12 and I take away 10, which is our mu, and I divide it by 2, and what does that give me? It does in fact give me 1. And what do you think we do then to our y value? Well, previously, where we multiplied by sigma, we divided by. So here, because we're dividing by sigma, we're going to multiply by y. So that's just going to be sigma y. So our coordinates of x, y now map onto x minus mu over sigma, comma, sigma y. Now these two things that I've written here are actually quite important. So look at writing those down in your notebooks or understanding what they mean, because life is going to be much, much easier. So if we can now take off all of our scribbles and go back to my general diagram, then if we look at our standard normal distribution equation, which is what we had before, function of x is equal to 1 over root 2x e to the minus of half of x squared, then we can now say that our normal distribution, so that's this equation here, has the general form of function of x is equal to 1 over sigma times the root of 2 pi times the exponent of minus a half, and in brackets x minus mu over sigma, all squared. Right? So that looks really complicated, but it isn't. Remember, this thing here was simply our x transformation, and this thing here was simply our y transformation, because we worked out previously that x comma y went to x minus mu over sigma, comma, sigma times y. All right? Now this is going to be the basis pretty much for most of the rest of the work, or specifically the formula that we've written down here. And in summary, what we're trying to do is looking at how do we go from our normal distribution to our standard normal distribution. Okay, so it's looking at how do we change whatever our normal distribution is to become into our standard normal distribution. Let's look at the idea now of standardization. And that is where we look at what values of probabilities fit between each of our standard deviations. We'll now move on to the idea of standardization. Standardization is quite an important topic because it helps us talk about data sensibly. Now we've already come up with the idea of the standard normal distribution is centered around 0 and has 1, 2, and 3 standard deviations on one side, and -1, -2, and -3 standard deviations on the other side. And I believe I've already mentioned that within 3 standard deviations of the mean, that about 99.7% of the data lies. Well, these aren't the actual only statistics or the only pieces of information that fit to the standard normal distribution. If we just look at either side of the mean with the first standard deviations, and that's say going from -1 to 1, then what we find is that 68% of our data fits within that particular scale. So if I was to draw a dotted line down here and a dotted line down here, then what we find out is that actually in this blue section here is about 68% of our data. Ooh, data. And if we look between the two standard deviations, so that's between the -2 and 2, we find out that about 95% of our data falls between. So again, if I dotted line around the 2's, and look now at shading all of this area green, then we find that all of this area would be around 95%. And that would mean that 99.7%, as we've already said, is between the third standard deviations. Now these values become incredibly important because they help us make some classifications or some serious statements about what data is written. So if we have an example where our mu is 100 and our sigma is 15, then what I can say is that, well, between our first standard deviations, or more importantly, 68% of our data, will fit between the values of 85 and 115. How do I do that? I literally do 100, I add on 15, and I take off 15. So between the two standard deviations, which we now know is 95% of our data, we actually find out that they will fall between 70 and 130. Again, how do I do that? I take 100 and I take off 30 and add on 30. Why? If one standard deviation is 15, then two standard deviations must be 30. And finally, between three standard deviations, which is 99.7% of our data, will fall between 55 and 145. Using this is quite powerful, but what if we don't have our normal distribution? What if we don't have our standard normal distribution and our graph is, as we've done on a previous example, somewhere else? Well, we can actually move our information. We can actually go from our previous graphs and say, well, okay, how do I go from my scores to standardized scores? And actually that's what they're called. They're called standardized values, right? Standardized values. And I'll put a Z in there for our American watchers, although that sort of offends me. Right, okay, so if we've got our standard curve here, just a quick sketch, and we know that that goes between 1, 2, and 3, and we've got our other values, which is much wider, and we've got our 10, 12, 14, and 16. Well, we know that actually to get from this value to here, because we did it in our first part of our video, was you take the x value of what you're here, this value, you take away mu, and you divide by sigma. And actually, that's pretty much what it is. To get our standardized scores, that's the equation. Take your x value, take away mu, and divide by sigma. How does that help us? Well, imagine we've got a scenario again where we have mu is 100 and we know that sigma is equal to 15, and we want to find out whereabouts in our graph the score of 97 fits. Well, if we now know we have our score of 97, then z, our z score, becomes equal to 97 minus 100 divided by 15. And using our trusty calculator, that becomes equal to minus 0.2. Well, where does that put us? Well, minus 0.2 will actually put us this side of our normal distribution. If you think about it, there is our normal distribution. We have 0 is our mean, and minus 1, minus 2, and minus 3. So minus 0.2 will put it somewhere in that region there. How does that help us with information? Well, we'll come on to that in a bit. But having known this formula here, the z score, or the standardized scores, are given by the x value minus mu over sigma, you're going to be able to have some pretty powerful mathematics in your hand. Apologies if you can hear random creaking and whistling. That's the rather interesting weather we've got outside in Melbourne at this moment in time. I'm pretty sure my apartment, if it doesn't collapse during the end of the day, it'll be a miracle. On to the next section. Okay, some good news. We're now nearing the very end of chapter 18. Not a lot to actually deal with. Let's go back to our standard normal distribution. again, just to recap, we know that this is centered around 0, and we now know that these Z scores, our standard scores, can be split up into 1, 2, and 3, -1, 2, and -3, and we know the various areas that fall between. Now, bearing in mind these areas deal with probabilities, and that's the whole point of this, is trying to find the probability of things happening. How do we use this to find areas under curves? Well, the great news is that we can actually use our CAS calculators. So, just to deal right into an example, if I had a question that wanted to find the probability of -1 Z 2.5, what does that actually mean? Well, the first thing is, when you see the letter Z, that is standing specifically for the standard normal distribution. That's a bit of a hint to us that we're going to deal with our mu of 0 and our sigma of 1, right? So where you see a Z, that's talking about our standard normal distribution. And if we drill down a little bit more into this, well, we've got -1, and we know that -1 is this value here, and we've got 2.5, which I think is going to be pretty much somewhere here. And effectively, what that question is asking for is, if I was to draw a dotted line down here, and I was to draw a dotted line down here, it would want to know the area between each of those standardized scores. Wow, that's going to be an interesting one to try and work out. How do you work out all of these areas? Do I have to integrate and do all sorts of horrible things? Well, if the question was feeling particularly evil, then maybe, but as I say, the good news is your CAS calculator can do all of this for you. So going into your normal Cdf function, what values would you put in? Well, it's going to ask you for 4, it's going to ask for your lower bound, an upper bound, a mu, and a sigma. And so in this situation, our lower bound is -1, our upper bound is 2.5, because these are the boundaries that we're trying to find the area. Our mu is equal to 0, and our sigma is equal to 1. Yay! Doesn't sound particularly difficult. And what does that come out with? Well, when I plonk it into my calculator, I get the value of 0.8351, which would suggest that 83.51% of my data fits between those two, or that 83.51% would fit between those two bounds. So there's a probability. Does it get any more difficult? Well, yeah, what happens if we actually wanted to find the probabilities between our x value? You know, where we had something, for example, between 97 and 115. Ooh, well, I suppose firstly we need to know our mu. Well, let's assume that's 100 again, and let's have sigma of 15. How do we find this out? Well, we know now how to go from our x values to our z values, right? So we could, realistically speaking, change this into z values and use our function we've done before. But actually, it doesn't need to be that difficult. Because the calculator asks for mu and sigma, you don't have to worry about any of this z values. You can use the same normal CDF function, and in this situation, you'd have your lower bound as 97, your upper bound as 115, your mu is 100, and your sigma is 15, and it does all the hard work for you. So that normal CDF function is pretty important. What if I knew the area under the graph, but I wanted to find a situation where I needed that specific probability, or that value, as it were? So, to be more specific, let's say I've got the probability of something happening, and x is less than or equal to k. And we want to find out what value of k was equal to 0.95. Well, what does that mean in English? Well, it's basically saying what value of k on my graph would have 95% of the information fit within it. Well, 95%, because it says this way, because it's less than or equal to k, is basically saying, well, if we draw a dotted line somewhere on this graph, I now know that this is going to be k, and I know that all of this area, all of it, from the very beginning to the very end, is going to be 95. Wow. Well, how do I find that? Well, if we had our z-scores or our standard, we could put in values, but luckily there's a function on our calculator again called the inverse normal, right? It's the inverse normal. And we simply put in the idea that, well, what information do I need to know? The area is equal to 0.95, and you enter it in as a decimal. It does all the calculations for you. It will ask you for your mu, and we could put in 100, for example, and our sigma is equal to 15. And in this situation, out will come our value. Does it get any more complicated? Nah, not really. there's one more thing we need to know. What if I want to find a range of values? So let's look at, we now know that we've got C1 and C2. Our range, we want to find about where C1 and C2 is to give us 95% of our data. Well, our calculator can't work that out because there are an infinite number of ways of squeezing 95% between two values. But if we were to assume it was symmetrically distributed, right, okay, so I'm going to draw a dotted line here and a dotted line here, and we now know that all of this blue area has to give me 95%. What does that tell me about the ends? Well, 95%, well, that's 100 minus 95 gives me 5%. So I now know the data in this end and this end must be 5%, or I've got 2.5% in each tail. All right, well, if I've got 2.55%, I can now actually find the value here that will give me 2.5% of my data. How do I do that? I use my inverse normal. So what values do I put in? Well, assuming again that we've got a mu of 100, and we've got a sigma of 6, then what do? Well, again, my area for that first calculation will come out as 0.025. Remember, you've got to do it in a decimal. I put my mu in as 100, and I put my sigma in as 6, and what would my value come out as? And again, I'm just going to state this, that what you would actually be finding is x is less than or equal to 0.025. And what happens when I put that into my calculator? I get that value as 88.240. Right, nice and easy. How do I find this value here? It's got to lie at 97.5% of my data. So this time I put in my area as 0.975, same mu as 100, same sigma as 6, and what does my value come out at? Yep, 111.760. So there we go. So I now know the value of C1 is equal to 88.240, and I know that C2 comes out to be 111.760. Okay, what I'm going to do now is just a couple of examples, again from the textbook, that sort of highlights the power and perhaps the ease with which we can now use the normal distribution and inverse normal functions to help us find bits and pieces. The question on the video is now pretty trivial, but it just gives an idea of what we need to do. So the time taken to complete a logical reasoning task is normally distributed with a mean of 55 seconds and a standard deviation of 8. So if I just have my standard distribution, we know now that it's going to have 55 as my mean and my standard deviation of 8, right? So that means that's going to be 63 and 71 and so on, and likewise the other way. Find the probability correct to 4 decimal places that a randomly chosen person will take less than 50 seconds to complete the task. Now, because this is not the standard normal distribution, it's a normal distribution, what we're trying to find then is the probability of x is less than or equal to 50. All right, so we're trying to find the area of the curve that will give us x is less than or equal to 50. So we go into our function on our calculator, more specifically our normal Cdf function, and what do we put in as our limits? Well, we would put in our lower bound as minus infinity. Remember, we want to go all the way back. Our upper bounds in this situation would be 50. Our mu, or our mean, would be 55. And our standard deviation, because it's given, would be 8. And if you put that into the calculator, then the probability comes out to be 0.2660. So the probability of a randomly chosen person taking less than 50 seconds is 0.2660, or 26.6% if we're going to do it that way. That was a nice trivial example, but it just gives you the idea of, using a graph. I have to draw these things personally. All right, I like to put on the mean, or I like to put on, some of the standard deviations just so I get an idea of where we're going. Then life gets more interesting because they tend to throw in a bit of a curveball. Let's look at the next example. Now, I won't be lying if I actually turn around and suggest this question took me probably about a good 20 minutes to do. Why? Yeah, that's a very good question. Why? Because it tricked me. And remember, maths is a big, fat trick. How did it trick me? Well, let's look at the diagram. We've got a very quick diagram here of what we're trying to achieve. So, limits of acceptability imposed on the lengths of a certain batch of metal rods are 1.925 centimetres and 2.075 centimetres. It observed that, on average, 5% are rejected as undersized and 5% are rejected as oversized. Now, if we now draw a diagram, what that is suggesting is, here is our curve. We now know that the lower bounds of 1.925, right, so this bottom section here is 5%, and we now know that the upper bounds, the ones that get rejected, are at 2.075, so this bit here is also 5%. It's now saying, you know, assuming the lengths are normally distributed, find the mean and standard deviation of the distribution. Wow, okay, so we don't know the mu, and we don't know sigma. So I'm going to write mu equals question mark and sigma equals question mark. Right, okay, well, we know that the bottom 5% fit into this section here. We know the probability of x being less than 1.925 is equal to 0.05, and we know the probability of x being greater than 2.075 is equal to 0.05. Now, from a previous video, if you remember, we don't tend to deal with things being greater than. All our functions on our calculators deal with less than. Right? We're dealing with the area from negative infinity and up. So I'm just going to write this one here, that the probability of x being less than 2.075 is equal to 0.95. And these two things now are going to become very important, or the things I've just put brackets around. This, not so important, so we'll squiggle it through. Now it's normally distributed, but I don't quite know how am I going to do this. There's no function on the calculator at the moment that tells me how to find from 1.925 being in 5%. But what we do know is that actually if we were to look at our normal distribution, right, and we were to say, well, where would 5% be for our z-score? What would our z-score be, all right, for 5% there? And what would my z-score be for the top 5%? Well, if you remember, we can find out z-scores, right, because we know what our standard distribution is. Right. Looking at the standard then, we can use our inverse norm. Right, we can use our inverse norm and we can say, well, we know the area is 0.05, we know that mu is equal to 0, and we know that sigma is equal to 1. Right, so that's our z-scores for where the bottom 5% and the top 5% of our distribution would be. Right, now if we actually do that, that means our lower z-score is minus 1.64485, and my upper z-score is 1.64485. If I write that onto my diagram now, so we know a lower is minus 1.64485, and I know the upper is 1.64485. How does that help me with these values here? Well, quite easily really, because we know how to get from our x values, we know how to get from our normal distribution to our standard normal distribution. Because if you remember, we have our z-scores are given by the value of x minus mu over sigma. So I know my lower z-score is here, is minus 1.64485 is equal to x, well we know the x value of that is 1.925, minus mu, we don't know what mu is, and divide that by sigma. So I don't know either of those. If I've got two unknowns, I need another equation. Well, I know my upper z-score is 1.64485. That's equal to 2.075 minus mu over sigma, and that's not a 6 by the way, sigma. And so having got this equation here and this equation here, I can now solve using my CAS calculator. And what do I get? Wow! Yep, very excitingly, I'm running out of room, so I'm going to do it up here. From my CAS calculator, I get my mu as 2, and I get my sigma as 0.04557. Now that's an interesting thing here. I'm just going to point out something of u equals 2. Because we could have actually found this out straight away. Bearing in mind this thing here is symmetrical. If I know it's symmetrical, and I know the bottom 5% is at 1.925 and the top 5% is at 2.075, theoretically speaking, or in fact actually speaking, if I add these two together and divide it by 2, that gives me my value of mu, which does equal 2. So it was nice to be able to have some clarification, but also useful to look at the idea of how to get from x, as in your normal distributions, into your z-scores to find out means and standard deviations. Well, that brings to the end of this video on Chapter 18. Hopefully it's made some sense. I look forward to seeing you on the next one.